just the most original, the so-called simplest. I mean, would be simpler than this, right? Because this is case theory.
Yeah.
And will you say that the tool works for that case?
In the simplest example of the Witten model, if I
no, Witten, not Witten.
Witten model.
Yes.
If I work carefully, then right, the Witten model is the model with superpotential, right? Yeah, and then some quantity can be computed as a sum over contribution from the critical point of the superpotential. Yeah, something like
so
that.
So the answer is yes. The technique works.
Yes. And
you can get an answer.
Yeah. Yeah.
Okay, go.
Yeah, yeah. But maybe for very restricted class of supersymmetrical samples.
Okay, please go.
Okay. So as we have seen, in some models of integral or path integral, we have supersymmetry, which is a fermionic symmetry exchanging bosons and fermions. Okay, so there is a supercharge which transforms bosons into fermion and vice versa. And there are many such problems of integral or path integral, but we are particularly interested in the supersymmetry which generalizes the Poincare symmetry or the symmetry of special relativity. Okay.
This Q is the same as the previous Qs, or not?
This Q is a generic supersymmetry. So in some field theory, we have more than one Qs with spinor indices or other indices.
So it's different from the previous Q of fermion equals 0.
In that sense, you can regard this Q as the same as the previous Q. Yeah, this is the same as the previous Q. Okay. And then in 4 dimensions, we have a notion of minimum supersymmetry. And the minimum supersymmetry is generated by, known to be generated by 4 supercharges. 2 of them are forming chiral spinor, and the complex conjugate of this is denoted by Q bar, and it's an anti-chiral spinor. Okay, and algebra they satisfy is given by this anti-commutation relation. So the reason why we are thinking about anti-commutator instead of commutator is that the supersymmetry is a fermionic symmetry. Okay, so this anti-commutator is what? The anti-commutator Q and Q bar is proportional to the flow momentum. And this structure constant is a representation theoretic quantity which transforms the product of chiral spinor and anti-chiral spinor into 4 vectors. Okay, so you may not find this formula comfortable, but in my opinion, this anti-commutation relation is not very much different or not very much more complicated than the ordinary commutation relation of angular momentum generator. Okay, so if we say that we are working with the supersymmetric field theory, what we are interested in is a kind of field theory on which this algebra, symmetry algebra, is realized. Okay, and there is a notion of n-extended supersymmetry as well. So for this supersymmetry, the algebra is generated by 4 times n supercharges. Now the supercharges have got additional level, capital I, which runs from 1 to calligraph n. Okay, and the property of this the n-extended supersymmetry is that the particles of relative spin difference up to calligraph n over 2 are combined into a single supermultiple, or the representation of the superalgebra. And the general property is such that as we increase the calligraph n, the structure for the theory is more and more constrained. So the phenomenologically interesting supersymmetric model is mostly n equals 1. Okay. But on the other hand, if we increase the number of calligraph n, we will be able to say a lot more about various quantities. So let me be more specific and focus on n equal to supersymmetry. And in this case, if you don't want to couple gravity to other degree of freedom, basically what we have is the gauge multiplet, which contains vector field or gauge field, or the matter multiplet, which doesn't contain gauge field. So in a gauge multiplet, we have a scalar Higgs field and the vector field and the complex conjugate of this guy and some fermions. And in matter multiplet, we have a scalar field, which we usually call quark, and fermions, which we usually call quarks. So we can consider gauge theory corresponding to arbitrary gauge symmetry, and we can couple it to a matter multiplet sitting in the arbitrary representation of the gauge symmetry. And since this multiplet structure contains gluon and quark, yeah, we can cook up something like QCD with n equal to supersymmetry. But unlike the realistic QCD, if we have n equal to supersymmetry, all the interaction among different kind of particles are specified by a single quantity, gauge coupling. So phenomenologically, this n equal to supersymmetric models are not very interesting, but still we can analyze this model to a great precision, and we can say a lot about the confinement property or electromagnetic duality property, and so on. So from this formal point of view, this n equal to supersymmetric system is very interesting. And as a simplest example, let me focus on the supersymmetric Yang-Mills theory, which contains gauge multiplet only, and let me choose SUN as a gauge symmetry. Okay, so this means that all the fields sitting in the vector gauge multiplet are n by n matrices. Then the microscopic Lagrangian is given by this. So this gives the definition of the microscopic theory. So here I neglected all the fermionic terms. So the Lagrangian consists of the Yang-Mills kinetic term for the gauge field, and we have kinetic term also for the scalar field, and here we have potential. And the last term is the term so-called theta term. So classically, this term doesn't play any role, but if we are interested in the quantum property of this model, we have to take into account the effect of topologically non-trivial gauge field configuration called instantons, and then in such cases, this theta term makes difference. And here, the field strength is defined in this manner, and the covariant derivative is defined in this manner. And at this point, I would like to introduce what is called the instanton counting parameter, which is the exponential of the complex combination of the theta angle and inverse gauge coupling. Okay? So this is the microscopic definition of the theory. And starting based on this, what we would like to do is to know in detail about the physics at low energy. For example, we would like to know what is the vacuum structure, or we would like to know what is the dynamics of light particle upon this vacuum. Okay, so this kind of question is what we often ask in studying various different kinds of quantum fields. For example, when we are interested in realistic QCD, we are given a microscopic Lagrangian consisting of gluon field and quark field. And starting from that, we would like to know, we wish to know about what is going to happen at low energy. Okay, about the dynamics of rich variety of hadrons.
Previously, you defined the critical point as by the equation delta psi, Q psi equal to 0, right?
Yeah.
So what are the critical points of this theory by that equation?
I'll come to that point later. Yeah. So before that, I would like to explain what the n equal to supersymmetric theory is. So please hold on. So for realistic QCD, this kind of question is very hard. So that usually
are they related to the so-called vacuum or not?
Sorry?
The critical point, your critical point, are they related to the so-called vacuum or not?
Or sometimes, yes. Yeah. Sometimes we have to include more than just a vacuum. Yeah, it depends on the choice of supercharge. Yeah. Yeah, so this enters into the detailed analysis. Yeah, so for realistic model, usually we have to study this kind of problem by putting the theory onto lattice and simulate. But when we have n equal to supersymmetry, thanks to this large symmetry, we can say a lot about the low energy dynamics of the model from just analytically. So first, let me work out the vacuum, which is nothing but the minimum of the potential. So you may think that vacuum is characterized by just phi equals 0, but actually this model turns out to have infinitely many degenerate vacua. For example, if phi takes this diagonal value, then obviously phi and phi bar commutes, so that the potential is vanishing. Okay. So as this argument shows, there are infinitely many degenerate vacua, and they are all labeled by the diagonal form of the scalar field in the gauge market. Okay, and we say that the degenerate vacuum are forming the moduli space of physically inequivalent vacuum. Okay, so first we have to notice that there are infinitely many vacua in extended supersymmetric models. Next, we would like to know what is the spectrum above each of the vacuum. Then we have to, on generic vacua, it turns out that the gauge symmetry is broken from SUN down to n-1 copies of U1. Okay? So this is what is called the Higgs mechanism. So this says that originally we started from SUN, n by n matrix valued gauge multiplet, but after Higgs mechanism takes place, what we are left with is just the n-1 copy of U1 gauge multiplet. And all the other degrees of freedom acquire masses due to Higgs mechanism. So this mechanism is the same mechanism as the W boson in the standard electrolytic theory, acquire masses. Okay? So we understand the structure of vacua and the spectrum of light particle upon each of the vacua. Then, what is the low energy dynamics of those light particles? Well, unlike the realistic QCD, if you have n equal to supersymmetry, by just assuming the existence of supersymmetry, we can say that the dynamics of light particles is completely encoded in a single holomorphic function of the vacuum parameter and the instanton vacuum parameter. And this very important holomorphic function is called the prepotential. And to be more precise, we would like to write down the effective Lagrangian for n-1 light gauge multiplet. And then the Lagrangian can be written in this manner. So we have kinetic term for scalar field and gauge field strength. And we have some quantity which plays a role of the gauge coupling here and here. And actually this tau ij is nothing but the second derivative of the prepotential. Okay, so as you can see, if you are given the prepotential, it determines everything about the low energy dynamics. Okay, so this is very much unlike what we know about realistic QCD. Okay, so but we need to know what kind of expression the prepotential take, and this is actually the hard part. So although we wish to determine the prepotential F for general gauge theories with n equal to supersymmetry, in general, this is a very hard problem. And the reason is that in order to be able to compute this, we have to take into account non-perturbative effect. So the loop analysis or perturbative analysis is never enough. And this problem is called the Seiberg-Witten theory because the Seiberg and Witten was the first one who was able to put forward the way to solve this problem. but before explaining how to compute this prepotential, let me illustrate what kind of non-perturbative effect we are expecting. Questions? Right. In Yang-Mills theory, we know that there is a non-perturbative effect due to Yang-Mills instant. So what is Yang-Mills instant? Well, the topology of the Yang-Mills field defined on four-dimensional flat space is known to be characterized by an integer called Instanton number. So k is the Instanton number, and its definition is given by this integral. And it's a remarkable property that no matter what kind of gauge field configuration I choose, this integral gives you an integer. Okay, so and the value of this integer is robust against any continuous deformation of the gauge field. Okay. And now we are interested in the configuration of Yang-Mills field, which minimizes the real part of this Euclidean action function. Okay. And this kind of problem can be studied by using a nice completion of square trick. And then the result can be summarized in this way. Okay. And then at the minima of this Euclidean Yang-Mills action functional, the gauge field has to obey either anti-self-dual equation, which is this, or self-dual equation, depending on whether the Instanton number is positive or negative. And the anti-self-dual equation says that the self-dual part is vanishing, and the self-dual part is defined by this equation. Okay. So this anti-self-dual field configuration is called instantons, and if the instanton number is k, we call k-instantons. And similarly, the self-dual configuration is called anti-instantons. So the rough picture of the k-instanton configuration is something like this. So since the number k is quantized, inside R4, there are k regions of finite non-zero instanton density. Okay. So these regions with non-zero instanton densities express the position of k fundamental instantons. And we can also try to evaluate the value of classical Yang-Mills action upon k instanton configurations. And then it, irrespective of the choice of gauge field configurations, if the instanton number is k, the value of the classical action is always given by this formula, q to the power k. And here, if you look at the expression for q, you notice that the g square appearing in the denominator here, okay, exponent is involved in 1 over g square. So you know that this quantity cannot be Taylor series expanded in. Expanded in the power series in the gauge coupling, so that everything which involves instanton is non-perturbative. So we cannot say anything about the problem of instantons from perturbative analysis. So let's go back to the problem of computing the prepotential. On general grounds, using the holomorphy, we can say that the prepotential consists of a term which is proportional to logarithm of q and the series in q. Okay? And the first part can be determined using perturbation theory, it turns out. But the second part cannot be studied by perturbation. So the determination of fk, the coefficient in front of the instanton series, is a very hard task. Okay? So this is the most difficult part of the Seiberg-Witten.
So this parameterization is some preparative contribution and instanton non-preparative contribution.
Yeah.
Are there some other class of non-preparative contributions to this f function?
From the holomorphy and on general grounds, this is the most general expression.
So the hard part is basically calculating fk, and that's coming from just related to Zhihong's question earlier about integrating over the phase space from a quadratic fluctuation. That's very hard because the different instanton number, the phase space gets more and more complicated.
Yeah. So the honest computation of FK is, we can imagine this to be very difficult because it involves a path integration of instanton backgrounds. So this problem was first solved by Seiberg-Witten, and their argument is not based on the direct path integration, but they made use of various mathematically sophisticated notions such as holomorphy or electromagnetic duality in supersymmetric gauge theories. And they also made use of a mysterious relation of this supersymmetric gauge theory to a theory of continuous deformation of the Riemann surface. Okay. Although their argument look quite fancy and beautiful, in some sense, this argument is so complicated and sophisticated, so that if there is a more direct way to evaluate this FK, it would be much better.
In your introduction to the instanton contribution, I suppose you are talking about the so-called, in the non-supersymmetric theory, the so-called dilute instanton gas picture, right? Now, could you tell us why that becomes exact? And what's the secret? What's the trick of it in the SUSY theory?
So later, in a few minutes.
Presumably, in the usual QCD, you encounter infrared divergences, right?
Yeah.
If you go beyond dilute instanton picture.
Yeah.
But here you don't worry about that, right?
Right. So part of the reason is that in supersymmetric models, the instanton configuration preserves some supersymmetry. And second, there is a very nice trick invented by Nekrasov that takes account of the problem about infrared.
So somehow the SUSY provides some kind of cutoff to the instanton size. Would that be a correct way of saying it?
No. We are introducing some totally different regularization scheme that takes care of.
No. I mean, in the usual dilute instanton gas picture, the problem is with the fed instanton, right? You encounter the so-called infrared problem. But here you do not have that, right? So I'm asking that somehow the SUSY, the magic symmetry, will cure that problem.
Yes, so that is the story I would like to explain in a few minutes.
And that means that SUSY somehow provide a cutoff to the instanton size, right?
Provide a cutoff to the instanton size. Yes, yeah. So essentially, we are implementing a very nice technique that only restricts the possible contribution to the instantons to those instants which have.
But I never knew before that SUSY would, give us good, the SUSY is intimately related to the infrared behavior. I never, I'm just ignorant. I never knew that before.
Oh, I see.
Is that okay, go on. Okay, maybe we could.
Okay.
I think you are talking about constraints, right? There's a size. That's actually.
Maybe Seiberg-Witten is correct. SUSY will help us in confinement problem.
Yeah,
but a priori, I don't see that. If you just look at the SUSY transformation, I don't see that. I'm sorry, go on.
Okay.
We are not in a hurry.
Oh, no, we are.
We are? Oh, I'm sorry. I'm sorry. We are. Okay, I'm sorry.
Right. So, so let me explain very quickly how to evaluate the prepotential, instanton contribution to the prepotential. So the first thing we have to know is that there is a nice trick due to Witten that transforms from n equal to 2 super Yamil theory to something called topological Yamil theory. So for that, we have to rename the fermionic field content from spinor to vector or spinor to a scalar and a self-dual to form tensor field. Okay, so this is the first thing we have to do to get the topological theory. And the second, we have to make sure that in renaming this fermionic fields, we preserve a scalar supercharge, and then we restrict our attention to the correlation function of supersymmetric or Q invariant operators. Okay. Then the next thing we have to do is to look at the action of this scalar supercharge, and then the action of Q on gauge field is giving this fermionic field with vector index. And what is more interesting is that the transformation of self-dual tensor component under the supersymmetry is just a self-dual component of the gauge field strings. So this says, if you recall the localization principle, that a path integral, infinite dimensional integral, localizes onto the moduli space of instantons. Moduli space of instanton means the space of solution to the equation f plus mn equals 0. And those spaces are labeled by the instanton numbers, k. So this observation says that infinite dimensional path integral reduces to some over finite dimensional integral over the moduli space of k instantons. Okay? Sorry that I'm rather quick.
So this k equals 0 is the perturbative part?
Yes. Okay. And actually, there is a very convenient parametrization of the k-Instanton moduli space due to Attiaji, Drinfeld, and Hitchin and Mani. So they provided, they showed that this moduli space can be parameterized by this set of complex matrices, satisfying this what is called ADHM condition and this equivalence relation. So these are rather technical detail, but essentially this property says that MK is actually a finite dimensional space. So indeed, the infinite dimensional path integral reduces to a finite dimensional problem of integral. Okay. So Nekrasov got interested in studying some kind of path integral formulation, which gives an answer for the generating function for the volume of the k-Instanton moduli space, right? And yeah, so he was looking for the path integral formulation which is suitable for computing this generating function. But you may notice that since each of the instantons can move freely around the four-dimensional flat space, naively this volume is infinite. And there are many other sources of infinity about this moduli space. So he thought that we have to implement some regularization scheme. And so he came up with a very interesting deformation of the topological Yang theory. He introduced a very special background so that the square of this topological scalar supersymmetry is not just 0, but the square of the scalar supersymmetry is this combination of the bosonic symmetry. It's a combination of gauge rotation and the rotation of the four-dimensional space. Okay? So the gauge field configuration, if it contributes to the non-zero path integral, has to be invariant under this symmetry. So that essentially it restricts the instanton to be zero size and all are sitting at the origin. That's the trick. And this quantity is called the instanton partition function. And this deformation is called the omega deformation. And yeah, okay, let me skip this transparency. And Nekrasov further was able to show that once we were able to compute this instanton partition function, then by thinking about this limit, actually we can compute the instanton contribution to the prepotential. So this formula is called the Nekrasov's formula, and as you can see from this property, we now regard this instanton partition function as a quantity which is more fundamental than the prepotential. So this contains a lot more information about n equal to supersymmetric case. And now the problem is how to compute this instanton partition function. Well, but since this instanton partition function is a generating function for the regularized space volume, we